Suppose you could. Does anyone care of getting greater homework back? Huh? Let's set a procedure that will satisfy all sides. If I do not return within 1 week, it is considered everyone gets it. So if I want to lower your grades, then I should rush. So now, if you accept this, then probably no one will complain on the way you evaluation forms homeworks or not returned. So you did bring something? Yeah. Okay, let's. Huh? You can try that. It will be covered.
Okay, well, I have.
Okay. So we'll try to get some procedures for getting back on schedule, but try to, even if you are busy and you do not know what to do, just get some effort. And do not hesitate to contact those who was doing previous years. And even better. So the plan for today's meeting is probably I will get a little reminder what we are doing, and then I will cover in more details what we did in the last 5 minutes of previous meeting, or technical details of which we will partially cover what was in the homework. The new material will be just 2 slides. So if you are aware of uncertainty principle, then you can see that. Before I get to the slides, let me distribute some materials. So there will be handout that I'm very late, so in some sense it is already obsolete. It was relevant a couple of weeks ago, but if your business courses evolve your life, you may enjoy reading this handout related to what we did in the past. So it was written by Nobel Prize holder Bishop Hyman, who was charged with teaching undergraduate physics, and he expressed did express the ideas of time propagation from his point of view. Another one, there was a little lengthy that I didn't print and send you by email. So it is looking forward into maybe next week, or how to interpret the mathematical results that we will get. So it's not for the past and the forward, but to the near future. So what in some sense, it reflects the homework and what we will cover now. And here I flipped it short page rather than double. This is also same subject. What electron in free space will be doing? It's predicting future of Gaussian vector in free space, authored by Schatz and Prater. They both are from Northwestern, and George Schatz is editor-in-chief for journals from physical chemistry. Some sense, number one. Oh, maybe some other people will disagree with it, but a noticeable figure. And also, this is a second opinion. If you do not like or catch some errors in the relation of the board or in the towards this, those are steps that will come to the right conclusions with hopefully no errors. I always knew that you are works. And let me offer something that we can tentatively schedule for coming Monday, but we can discuss it if you find necessary a couple of days more to do it. But this is too early to leave, and we'll just distribute because we need to come through some of the materials. And I think I have good intentions to type it in so that you will enjoy it. Okay, so who we are and what are we doing? So it is a physical chemistry class. We do want to get some background for predicting outcomes of measurements, because chemicals, materials, molecules differ by their properties, and in the simplest way one can look or smell or look how it appears visually, and in more advanced, more safer case one places the samples in instrument and measures some characteristics. And this course to some extent provides background for the measurements of the properties of materials. So in molecules we do have fully defined and negative electrons with respect to nature. We already got main laws of the wave of electrons. We know how to the future, but this knowledge, although very correct, is needs a little training so that you can apply it to different models. And these skills of applying laws of quantum nature of electron to different potentials in our sense, different shapes of potentiality, will be a substantial part of the course. So right now we are looking on the simplest possible problem, one-dimensional electron in which is alone in a space where there is no potential and kinetic energy. And to be certain, we set up initial condition as Gaussian well distribution in space, and we pose a goal to predict what will be the future of this vector. Before we start calculations, we assume from common sense that center of the vector should stay still or move with constant velocity, and the width should expand. Although we do not know for sure. Maybe it will get some waves, maybe it will shrink, but we are going to get through it through mathematical procedure. So we do have three ways of predicting the future by now: evolution operator, discrete finite differences, and eigenstates expansion of the equation. We are practicing eigenstates expansion of the equation. In order to run this approach, one needs eigen energies, eigen functions, and expansion coefficients. Expansion coefficients are convolution of initial condition, which is with all possible eigenstates, which are values in coefficients. So for practicing this, we need to take two intervals. First, we need to find this expansion coefficients, which of course we are over. The second integral is upon multiplying each of the expansion coefficients from the eigenfunction and time evolution factor, we need to integrate it over k, wave vector over the index, and then combine it back into Cartesian spatial space. Let's see how it will work. No surprises. It is what you were thinking all the time. I'm sure you have much more interesting things to think about. So, let's go briefly, not in all details, over the homework. So, some of you completed the question number 0 with definition of rate. So, this is needed for electronic signal processing, for digital sound that build this around, because if one, the sound is oscillations of their motors, and if one records it in an analog way, it will be just intensity of magnetization of the tape or whatever, and then chance for errors is very high. If instead of recording time-dependent intensity, one will just record the intensity of wave with certain frequency in a digital, one can drastically improve the quality. And anything that we hear right now is mostly digital. If you want to enjoy analog sound, probably should push the AM radio on your car. And Fourier transform is the way of converting this oscillating stuff, which can carry a lot of noise, into precise digital form. So right now we are looking not in time distribution but space distribution. So the function of x, which is when we explaining the summation of basis oscillating functions with all possible frequencies, what here is possible those wavelengths. And then the only thing that we change are expansion coefficient, which are percentage, how much wave of certain frequency enters into this. If you take analogy with sound, it will be one tone, one button, music instrument, then all components except one that corresponds to the right frequency will be zero. For resulting, we generate just one function. There are theorems how code is not that any good periodic function can be expanded to the sequence. This is more traditional way where everything is real, but very soon, I'm just commenting on that. Very soon there is a generalization of this Fourier transform towards the complex numbers, where the function itself and the coefficients can. So, example is periodic function, and it is selected just because it is easy to solve. One can live in doing differential equations or there is another course like partial differential equations. So there is a standard set of cohorts where one gives different shapes to periodic functions, triangles, and then the task is to find the coefficients. So there is a period, which means one needs to look only in a small fragment function because the rest will be the same. And this is just mathematical expression of what it shows. Give me a sign if I should talk with details, or give me another talk or do not talk. Okay. Yeah, so here's the definition. With the transform, we need to find these integrals. And right now you see that there are the integrals generally are from minus to plus. But since it is purely a function, one can integrate only from the limit that is right. And since the function is 0 for the half also period, one can consider the integral under in this part when you take a prime and go here the double. Will be integral from 0 to 2 between this integral and we see that the second integral will be 0, so we will not need to waste time. And in the first integral, it is 1, so we are, instead of function, we just integrating the sign. Right? I'm not going to write everything down, I will practice laziness, but cosine is even and sine is odd, right? So half of this integral will be positive, half of the integral will be negative. Therefore, if you take the error is 0 for the first problem. When we will do the same thing for sine, then in this area, we integrate sine from 0 to half period. If you coincide with the stuff, then it will be positive. But if it will be double frequency of the sine, then it will go up and down, and then it will be again positive. So all cosines should be zeros, and sines will be negative. Positive, 0, positive, 0. Right. And then the answer, I'm not showing it here, but it is A0 will be a constant half, right? 1/2. And A and even 0 zeros, E and constants that get smaller and smaller as we go further. I will not remember it, but it will be 1 over n plus 1 over n square or some progression. So for 4 equals 0, 4 even will be a progression that get smaller and smaller. And the meaning of this thing that if one adds together this science and this science, one will produce the function. So if one adds everything together, then it will be a function that will not be literally equal to original function, but it will be approximate representation. What about the question number 2 was simple copies from the notes, and this 3-1 was taken in those. Were there problems with last these questions?
How did you know what to use? Like what function?
Were.
Like rid of Riemann?
So the protocol for finding expansion coefficients is integral of eigenfunction times wave function time equals 0. Agreed? No complaints about it. Now, we are speaking not about any general problem. We have a specific problem where Hamiltonian is only kinetic energy. And gives the time independent Schrödinger equation gives phi sub n when waves are orbitals for this specific Hamiltonian. So if the Hamiltonian as simple as only kinetic energy, then orbitals will be just plane waves. Right? So these plane waves need to be plugged into this description. So integral dx d x. And then here we put the initial right. So it is the reason why we formulate integral this way.
So object. In the email that you sent out, there's.
Oh, there were technical details how to take this integral.
But where does sigma?
Sigma is good. So we assume, unlike math, a lot of part of the courses are hypothetical suggestions. Right? And we hypothetically suggest that at time 0, the wave function psi equals this E minus x squared over sigma naught, and sigma naught is width of this Gaussian distribution. So it is our, so to say, free Wallows decision to take, which sounds reasonably scientific. So you're okay with general direction. Okay. And then the rest is math, how to take this this integral. Whew. Okay. So where are we going to arrive if, well, I was thinking too positively on amount of free time, but we'll run out quickly. the goal is to get this expression either by copy pasting from handouts and textbooks or deriving ourselves. But again, we are not in a math class. All these math exercises are just tools. The main thing is to interpret. So when we practice motion of the single electron in one-dimensional free space, we do see that, well, I'm kind of looking forward, we will see that the probability distribution will keep Gaussian shape, but the width of Gaussian shape may change. On one. On another hand, in your homework, and in the quiz that you have completed last time, you do show that expansion coefficients that I kept writing are proportional to the minus a square secant. So I was just copy pasting from another. But I agree, I like this answer. And they skip coefficients. So this also looks like Gaussian function, right? But it is Gaussian function as a function of wave vector. The only difference that the width parameter is not in the denominator, but in the numerator. It's the same concept. And now, for the momentum space, the interpretation is opposite. So in Cartesian spatial space, the larger the sigma, the fatter, the broader is the wave. In momentum space, the larger the sigma, the thinner is the wave vector. In the K space, the bits which we can call sigma p or sigma k will be inverse or divided by sigma mu. Right? And we introduce two variables. So I'm going to say something very simple that I even feel guilty to say to smart people, but I apologize. I will say something very simple. I just rewrite this equation in a simplified way. So I can write it as E minus P squared divided by sigma. And then sigma P will be 4. So I didn't write. It is agrees with what you did in the whole, right? So if I love standardized way of Gaussian wave functions, I can put minus independent variable squared divided by width parameter. And since we are in the momentum space, I can call it sigma sub p. Right? And we see that the sigma sub p is inverse to our original sigma in coordinate space. Let's say sigma x. So the width of the wave packet in the spatial space at momentum at time zero. Good. And now we do, so this is obtained just by practicing math, by taking this Fourier transform. But now, if we see that they are related in a certain way, why don't we say that product multiplied left and right by sigma sub x? It looks like product of bits of the wave packet in the momentum space times bit of the wave packet in the spatial space will give something reasonable. Constant or maybe some slowly varying reasonable function. Please object if you do not like this. You do not object, so you agree. Right? So two Gaussian wave packets. And in momentum space and in Cartesian space, spatial space. And they both have width parameters. And product of this width parameter in different representations in different space are related to each other. Their product will be something valuable. So if we do not have time evolution, if you look all the way at time 0, then it will be constant. And where over 2 comes from careful account of all dimension factors. Right now I just skip them whenever is possible. So if we look just in product of two conjugated wave packets in spatial space and momentum space, their product will be constant. And if we carefully continue to solve the problem that we are solving, we will observe that the shape in the momentum space doesn't change, and shape in the Gaussian, in the Cartesian, in the spatial space will remain Gaussian with increasing width. Then the product of these two width parameters will grow. So in addition to initial constant, there will be a factor that changes with time. Okay? So we will get it from calculations. Yes? No. It's not cross product. It's just product of two numbers. Those are neither vectors nor tensors. I can put there a dot, but it is not a dot product. It's just simple multiplication. So our observation is that these two parameters, if multiplied by each other, will either give constant or their product will grow with time. And this is partial observation for one-dimensional free electron in free space. But this relation has philosophical sense. It holds for any other potential, and it is called uncertainty relation. Why we do use the word uncertainty? What is your interpretation? I'll keep on this messy slide. The most important thing is just to check. Yes. So we have a center of the Gaussian function. And if it is infinitely thin, if the sigma tends to 0, so it will be infinitely sharp, thin function, which means that we know for sure with big confidence that the most probability to find electron is at the center. It is certain. If you have broad distribution, it means electron may be here or there depending on its mode. So there is an uncertainty of this. The larger sigma parameter, the bigger is uncertainty. Now let's look on the momentum space. If this sigma sub, what we call sigma sub, goes to 0, then in momentum space it will be infinitely sharp distribution. which means that we know for sure P momentum of and if it will be sigma sub P will be larger, it means momentum will be unknown, uncertain. There can be variation. So the observation of the connection between these two functions, or then now it's time to wake up. So the product of uncertainties, the position and momentum, is not independent. It's either constant or growing function, which means that there are no setups in quantum world where both position and momentum can emerge simultaneously. So if you know for sure the position, it means momentum is very unknown. Can be anything. If you know for sure the momentum, it means the position is unknown. And we are coming through your successful formula, just through taking this in. So you see, it's not an axiom or postulate that we bring in. It's in some sense your derivation. And we did show it for a very oversimplified problem, but if you code for any setup, and even for more than for broad variety of variables, not only position and momentum, but there are other conjugated variables that can be measured with arbitrary precision simultaneously. So there is, if we are in classical world, if you're driving a car, each point of time we know where it is, we can measure the speed. If you're in quantum world, if the speed is measured literally, then we do not know where the car is. It can be either here or in the mountains. If you know for sure that it is parked here, it means that it may have simultaneously plus and minus 100 miles per hour. Which it contradicts with common sense, but here we have from math or from world it is a standard situation. Okay, now you can relax if you don't want to concentrate all the time. I will mumble some other things, but it is the main message of this. So, if we didn't know this distribution in momentum space, if we do want to predict future, we need to take this integral, and in the homework you are taking integral over space. Now we take integral over momentum, over wave vector. And I'm going to, we briefly discussed it last time, but I will briefly discuss it once again. So, how one can take this, and if you have this set before the same procedure, which just different direction from x, okay, and now we go. So there are three. In the homework there were 2 exponentials, now there are 3. But if we merge them together, because both this and this are k-squared, so it will be the same polynomial for the second column. And you can call whatever is in front of this coefficient as n. Now, how to take this? Okay, square integral of the Gaussian function will be square root of pi, and I will be, if anyone doubts, I will be very happy to prove it. It's one of the very few things that I can prove without preparation. So pi gets pi, and then since we go from 2-dimensional to 1-dimensional space, I need to put square root of pi. I will try to rush right now, but give me little signs should I ever return to this. Okay, good. So there is a. Some people think that it is quite true. So if you want to hear this from me, approach it right. I can send it. Okay. So we do know that the Gaussian integral is square root of pi if it is finite integral from minus to plus infinity. But the stuff that we are taking is a little different from this shape. So we need to convert this shape into this shape. Okay? And we can do some transformations by redefining everything that is in the power of exponential as new variable. So something that will be like a combination of a and a squared. By the way, square root of a can be put inside the brackets. So we have square root of a times k, and then everything squared. Then we can identify a full square if there would be a third term, right? A square k times this part, and then there should be the third term, right? It is not present here, but you can artificially bring it in. And if you bring it in, we need to subtract. So if you have only this part, we can plus and minus this term. So we can plus, and here is e to the power minus b squared. Since e to the power minus b squared will be consisting only on constants, not on the integration variable, we can put it outside of the integral. And here there will be the integral of simple stuff. I redefine this here once again. So the next step is to redefine a new variable. So if we call whatever is in the square in the power of exponential as new variable, then one would be able to take the integral. And our original integration is over wave vector. But if we take integral over dy, then this increments in these variables will be different by proportionality condition, which we should also take care of. So after taking the Gaussian integral, the result from integral will be only square root of pi, and the answer itself will depend only on free coefficient and this stuff that we multiply it in to generate the very defective square. And then one can roll back into original notation. So this b squared will be composed of x, which ix, which need to be taken squared, and square root of a, which includes original width and another term that originates from accumulation of force. So if we put it in, this term, this A, is what will be responsible for the uncertainty. So when we take B squared, then we will have this one in the denominator of the Gaussian distribution. I times I will give negative sign, and this part in the denominator will give the uncertainty. There is a little thing that you may catch me, or thing that you found in error. Here is the square root of A. A is linear in time with imaginary unit. So if we take B squared, it will have denominator linear in time with imaginary unit. And in the uncertainty, we were talking about t squared, and it was all real, right? So do you see where is the problem, or where is the solution? Huh? You can multiply. I like the direction of the thought, but can you be a little more certain? So wave function itself is not, no one observed. There is an interpretation of wave function squared, or wave function multiplied by its conjugate. So in fact, we need psi times psi. And if we take conjugate, so we need to take this function multiplied by itself, and in one replica it will be with negative I, and in another will be with this plus.
That's what I was trying to say.
Yes, yes. I identified that you were saying correctly, but it starts that you need probability distribution. Okay. No, 1 minute. Well, if one carefully, without taking square, it will have imaginary. But if you take absolute value square, then one will arrive at this result. So I'm skimming through details. So multiplying a plus b times a minus b will be a square minus b square. And since one has imaginary unit, it will be plus here. So for probability distribution, it will be sigma naught, and here will be proportional to second power of n, which means that bits will grow quadratically, and product of uncertainty of position and momentum will grow quadratically as well. Whew. Therefore, we have, it's just product. We prove that simultaneous uncertainty in position and momentum will be larger than constant. Thank you for the patience. Looking forward to see you on Wednesday. Who didn't install MATLAB on the personal equipment? Who did install? No one? It's not mandatory. You feel free to do as comfortable as you wish, but your life will be a little easier if you install.